Go ahead.
So thank you so much for the introduction, and thank you for the invitation to be part of this BCI and Unity Masterclass. It is a truly pleasure to be here. And hello everyone, my name is Ana Martín Fernández, and I am a PhD student at the Biomedical Engineering Group at the University of Valladolid in Spain. And today I will be sharing some of the research that we are carrying out in our group regarding c-VEP-based brain-computer interfaces. Specifically, I'll be presenting the c-VEP Speller app, which we developed within our Medusa software ecosystem, with Unity playing a key role in its design and in the app implementation. So to give you an idea on how this session will go, here you can see the index and all the content we will be talking about. First, we will start with a brief introduction, just to make sure we are all on the same page about what c-VEP-based brain-computer faces are. Then we will move on to the Medusa software ecosystem. We will see an overview of its architecture, and specifically, we will see how Unity applications are integrated within the software. After that, we will move onto the third part, which is talking about c-VEP Speller app. We will see how it is implemented and a bit of its architecture and functioning. Finally, once all this is understood and everything about the system has been explained, I'll share some of the research that we are currently conducting within our group. And also, of course, at the end, we will have some time for questions. So let's start with the introduction. Over the past few decades, direct interaction with the environment through brain activity has evolved from a concept and just an illusion to a practical reality. Driven by advances in communication technologies and neurotechnologies, brain-computer interfaces emerge as systems that enable users to communicate and control external devices just by using direct brain signals without needing any muscle activity or peripheral nerve activity. And BCI systems operate in a closed-loop architecture, which is composed of several stages. So first of all, we need to acquire the user's brain signal. And for signal acquisition, the most commonly used neuroimaging technique is electroencephalography, or EEG. Due to its non-invasive nature, its portability, high temporal resolution, and also its relative low cost compared to other neuroimaging techniques. Once we've acquired the signal of the user, we need to move on to the next stage, which will be real-time processing. At this stage, we will perform feature extraction, feature selection, and feature classification, allowing the system to interpret that acquired signal and to decode what's the user intention. And once this signal has been processed and that the intention of the user has been decoded, some command needs to be executed. That means that the decoded signal will be translated into a specific action, which could be controlling any device or any application. And finally, the fourth and last stage of that closed loop will be the feedback. The user will see how his initial intention has been translated, and this will enable the users to refine their mental strategies in case the output received was not what was expected or didn't match the initial intention of the user. So given the great potential of these kind of systems, several applications have been explored within the BCI literature, and some of which include, for example, stroke rehabilitation therapy. Some motor imagery-based BCI systems have been implemented to restore motor and cognitive functions in patients that are recovering from stroke. Another application that's been explored is cognitive training. Some neurofeedback-based BCIs have been used to enhance various cognitive abilities, such as attention, concentration, also relaxation, and working memory, for example. Also, other of the main applications being explored has been device control. Different BCI paradigms have been explored to enable control of external devices, for example, wheelchairs, prostheses, robots, or even home automation systems, providing in that way the users with an additional degree of freedom and with hands-free additional degree of freedom. However, in this session, we won't be talking about any of these applications, and the BCI application in which we will focus and the one about we will be talking today is the speller, one of the main applications explored since the early days of BCI research. And this application provides users with an alternative means of communication, allowing individuals with severe motor impairment to express themselves, to interact with others, and in doing so, they can offer greater independence to these patients and also improve their quality of life. So, as I've said, this is the application, the BCI application, in which this talk will be focused. To better understand how BCI system functions, we will need first to clarify what control signals are and why they are essential. We need to take into account and to understand that directly translating high-level cognitive processes such as thinking into actions is not feasible. Also, that EEG signals have a particularly or quite poor spatial resolution and are quite noisy, which further limits the interpretability of these signals. So to overcome these limitations, BCIs need to rely on well-defined signals, which are known as control signals, that are generated as a specific neural responses to some experimental paradigms. These experimental paradigms are designed to elicit synchronized neural response in large group of neurons of specific brain regions. Thus, the produced signal can be reliably detected and interpreted in order to interpret what's the user intention and what is the intended outcome. So, depending on the origin of those signals, they can be classified in endogenous signals and exogenous signals. Endogenous signals are those that are internally generated by the user without the need of any external stimulation. And on the contrary, exogenous control signals are the ones that are produced as natural neural responses of the users in response to external stimulation. So, for example, examples of endogenous signals will be a neurofeedback or sensory motor rhythms. Then, halfway between both groups, we found P300 evoked potentials, which involve both endogenous and exogenous components. And finally, as examples for exogenous control signals, we have a steady state visual evoked potentials and code modulated visual evoked potentials. And these exogenous control signals are the ones that are mostly most commonly used in the implementation of spellers, of BCI spellers. So therefore, they are the ones in which we are focusing right now, and all the work I've been discussing will be relying on that kind of signals. And specifically in code modulated visual evoked potentials, or c-VEP. These control signals are visual neural responses that are primarily generated over the occipital cortex as a reaction to flickering stimuli, encoded using a pseudo-random sequence. For instance, here we can see an example of a binary pseudo-random sequence. In here, you can see the binary pseudo-random sequence, and what is happening is that depending on the bit, if either it is a 0 or a 1, this will be translated into a white or black color of the stimulus, producing that flashes. And to obtain this response, one thing that is very important is that this stimulation, this visual stimulation, occurs at a fixed rate, which typically will coincide with the monitor refresh rates, which are at 60 or 120 Hertz. To encode multiple commands, what are the sequence, the pseudo-random sequence that is most commonly used are M sequences. And these sequences are particularly suitable for this purpose because they present excellent autocorrelation properties. With maximum autocorrelation when the sequence has zero lag, like meaning no time shift, and which we will refer during this presentation as the original, let's say, M sequence. And then it has nearly zero correlation for any time-shifted version of the same sequence. So this characteristic will allow to encode multiple commands with the same sequence, with just one sequence, and temporarily shifted versions of it, which is what is known as circular shifting paradigm. And now we will take a look on how any c-VEP-based BCI relying on the circular shifting paradigm works. And mainly its workflow is divided into 3 stages. First, we need a training in which the system will be calibrated for a specific user. According to this training data, a template creation phase will occur, in which templates are created for this user, and then the user is ready to use the app and test it in online mode. So here we can see with a video, this is what calibration or training phase looks like. The user has to focus on that command with the original sequence with no lag for a predefined number of cycles. For now, from now on, I'll be referring to cycles to say a complete repetition of the M sequence. So after this, the user looked at this, we will evaluate its response to achieve the templates. So the signal we have acquired will be analyzed, averaging the different cycles and repetitions of the sequence, and especially filtering it through a canonical correlation analysis, which will produce us the template for the first command. We've just calibrated with one command, so we acquired the template for one command. But what we can do is to temporarily shift this same template as many bits as we want to, or we need to obtain the templates for the other commands. So if you look here at the red points, you can see that all these templates have the exact same shape, and what is different is the lag they are presenting. The red point shows the same peak in all the templates, and we can see how it has been shifted from A to C. And finally, once we have all these templates created, the user can use the application just for a practical use. And in here, the user decides where to look, and its EEG signal in real time will be compared to all the templates we have calculated during calibration. And the command boost template shows the highest Pearson correlation is the one that will be selected as the user choice. So now that we have a clear understanding on how c-VEP-based BCI works, it's time to talk about Unity and why it's so important in the implementation of applications such as the spellers. And basically, there are two main reasons why using Unity provides significant advantages in the development of those applications. The first reason is that Unity is a robust tool for building interactive applications. It greatly simplifies the design and organization of graphical user interfaces, which in our case will be the layout of the speller. And in addition, the engine of Unity is optimized for real-time rendering and data input handling. And also it allows for communication with other softwares and other devices, which is quite important for our applications. So all these advantages of Unity helps to build an attractive and immersive application, which is so important if we want user engagement for our BCI application. This was the first reason, and the second reason why Unity is so important and so useful for building these applications is that Unity provides us precise control over the monitor refresh rate, and it allows us with a high temporal resolution to control frame rendering and monitor refresh rates even down to milliseconds. And as we said before, in c-VEP simulation, it is quite important to have a fixed frequency of stimulation. And it is really important that each bit of the pseudo-random sequence appears at an exact and evenly distributed interval of time to maintain the synchronization between the visual stimulation and the user neural response. So Unity allows us to control this feature will be a mandatory requirement to build a c-VEP-based application. So having all these ideas clear, we are now moving to the second point of this presentation, which is talking about the Medusa software ecosystem. Medusa is a software ecosystem designed to facilitate and accelerate the development of BCI applications. The software provides a range of advantages, including open source availability, which promotes transparency and collaboration between different research groups. Then it is is compatible with many hardwares through the lab streaming layer protocol. It presents a modular, scalable, and flexible design, which helps to adapt to different research needs and to keep it continuously updated. Then it relies on a pattern-based signal processing, enabling robust data analysis, and a Unity-based graphical user interfaces, which is ideal for, as I was just saying, create interactive applications and visually rich environments. Also, within Medusa, you can find a comprehensive suite of BCI experiments already developed and ready to use. And finally, if you want to develop new tools or new experiments, it also offers some material for that development and for sharing it and enrich the BCI community with distributing new applications through the app market. The three main components the software has, this software ecosystem has, are first of all, Medusa kernel, which is a Python package for EEG decoding. Then the Medusa platform, which is the graphical user interface that runs the experiments and is where all the applications will be managed, configured, and all the experiments will be managed through this platform. And finally, we have the website, which contains the documentation and the app market where the different experiments can be downloaded. This was published in the scientific paper in 2023 in Computer Methods and Programs in Biomedicine. So there you can find additional details about the architecture, the design, and everything you're curious about the software. You can find there all the information about it. And regarding Unity, one of the main advantages that Medusa offers us is that it provides a framework and detailed guidelines for developing new applications. And in particular, it includes templates for creating Unity-based applications, which greatly simplifies the development process. Because the templates offer already the scripts for a fully functional application, the developer will only need to adjust a few lines of code to adapt the template given to the specific research need or the experiment requirements. But there's already a solid backbone in which you can rely. And on this slide, we can see first in here the link to the web documentation where the process for creating apps based in Unity and where the process is described. And then in here we can see an image of the Medusa platform. And by going to and navigating to Developer Tools, Create App, this window will appear. And by choosing the Unity project template, we will create this project, including all the necessary files, both in Python to process and the EEG data and the files for the Unity project to generate the graphical user interface. Right now, I will show you like the project, the files that are created within the Unity project when a template is created, app using this template is created. First, we have the log2 file. This script defines a class whose job is to capture every message that is sent through the debug log and write it into a file so we can keep record of all the debugging and runtime messages. Then we'll have the manager, which controls the life cycle of the Unity app. Then the Medusa TCP client, which implements a class to establish connection with the platform and allows for communication between those two ends. And finally, we have the message interpreter, which defines a class responsible for the decoding of messages sent from the Medusa platform to the graphical user interface developed in Unity. So as I said, Medusa platform, which is Python-based and specifically within the kernel, we have all the functions to manage EEG data processing. But within Unity, we have everything related to the graphical user interface and the appearance of the application itself. So we need these two parts to be communicated. And for doing so, we use the TCP/IP protocol. This is a communication protocol that defines a set of standards to establish communication between different devices and allowing to share packages of data. So, and this connection has three main characteristics. First, it is asynchronous, meaning that data can be sent at any time without needing synchronization between the sender and the receiver. Then it is bidirectional, so information can flow in both directions between the two systems, and it is a full duplex, allowing data to be transmitted and received simultaneously at any time on both sides. So in our setup, this will be translated into Medusa platform, or the Python side acting as the server, and the Unity part of the application, the graphical user interface, acting as the client. And these two parts are maintaining continuous communication throughout the entire execution of the applications. So within the Medusa ecosystem, we can find our c-VEP speller app, which is the one in which we will be focusing for this part of the presentation. First of all, I'd like to clarify that the application is publicly available and can be downloaded for free from the app market on the Medusa website. And here you can see the app. And taking a deeper look into it, we will start talking about the applications in this diagram, which summarizes both the architecture and the workflow of the application. First, on the left side, we can see the architecture of the application. We have in here first the Python side. Here we can differentiate 5 modules. We have the settings module, which defines and manages all the application's variables. Then we have the constants module, which defines all application possible states. Configuration module, which is a graphical user interface that allows the users to manage all the variables for any application and to customize the variables for the given experiment. Then we have the main module, which controls the life cycle from this side of the application, and the controller, which is the one which will manage the communication with the graphical user interface in Unity, which is the one which will be sending the parameters to Unity and being in continuous communication with that other side of the application. And then here, referred to c-VEP speller graphical user interface, we have the Unity part, which will be a project with having all the files and the modules we've previously seen, also the Medusa TCP client, the message interpreter, and the manager for controlling the life cycle of the application from that Unity side. And as we have seen, these two parts are in communication through the TCP/IP protocol, being Python the server and Unity the client. And now, moving to the right side of the image, we can see the workflow of the application. First of all, we will connect through the LS stream to set up the EEG and to connect our EEG device to the platform. Once we have this, we can configure the application to adapt it to the experimental needs. And finally, when we run the application, the following workflow will occur. First, the app is powered on. Then when the user press the button play, the app will start, and once the app is started, the user have two options. Each time the app is running, the trials will be processing, and when the user wants to finish, it can either pause it and then resume it, or if it wants to finish it, it can press stop. So Unity will close and the data will be saved to power off safely the system. And now let's take a look at the Unity side of the application, starting with the scene description of the project. Here we can see the hierarchy of the different game objects that make up the scene. All the visual and interactive elements of the application are organized under a canvas parent object. This canvas contains many different child game objects, including the background scenario, the matrix of commands, the information and result box, and so on. And together, all these will form the user interface of our speller. Going through the different elements one by one, let's start with the canvas. The canvas is all the area where the user interface elements must be placed. It acts as a parent object for every graphical element that is placed into the scene, and Unity automatically create an object like this when any user interface element is created into the scene. This it appears as a rectangle in the scene view, which makes it easier to position and organize the elements visually without needing the game view. Canvas are particularly useful for building 2D interfaces such as menus or control panels, and in our case, it provides definition for managing the 2D speller layout. In this image, the red rectangle represents the area covered by the canvas. And we can see also that the first child object within the canvas, which is the background image, masks exactly this same area, which is the complete rectangle and all the background of the application. So this background is user interface image object, which allows to display either any color or a custom background loading any images behind the speller matrix and behind our commands to be selected. The next child objects we have appear on the top part of the interface and are the result box and the frames per second monitor, which are both informative elements. The result box displays the selections made by the system when the speller is running in online mode. So it is like typing the different letters that the user is selecting and writing the message on this top bar. And then at the right top corner, we find the FPS monitor, which indicates the current refresh rate of the monitor, which allows us to verify that the stimulation is being presented at the correct frequency. Next, we have the information box, which, as its name suggests, is an informative element. Its purpose is to indicate the current state of the application. It will initially display loading while the configuration parameters are being processed and are being applied to the scene. Then it will switch to waiting to start until the user presses the play button. Once the session begins, it will indicate that it is starting. And then when the run is completed, it will display run finished and closing if the user presses the close button. Obviously, while the run is in progress and we have all our matrix with all the stimulus flickering, this information box is hidden and it will not appear so that it doesn't interfere with the stimulation. And finally, we reach to the core element of the scene, which is the matrix of commands. The matrix is represented as an empty parent game object that contains the different commands. Initially, it will only contain a single cell, or each cell will be a command. So we have the cell, which has its own child objects. First, we have the child object of the text, which will be the letter A and is the label of the command. And then we have another child object, which is a point. It particularly is a midpoint that serves as a fixation point to help the users guide their gaze to stay focused on the command they want to select. The cell itself is implemented as an image, and the flickering effect is achieved by alternating the black and white color of the image according to the pattern of the defined M sequence. Now we will move from the scene to the manager. which is the main script of the project and responsible of controlling the life cycle of the Unity application side. And the code within this script can be roughly divided into three main sections. First, we have the Unity lifecycle methods, which are run on the main thread and include standard Unity methods such as awake, start, update, or fix update, and so on. Second, there are some communication functions. As we've seen, configuration and all the processing is handled within Medusa in Python, so Unity needs to be communicated with this server, and the manager needs to interpret those messages and to adapt to this information being sent from the platform. And then we will have the train and test loops that will organize the application behavior during those specific states when running the application in train mode or in test mode or online mode. One thing to note in here is that although they are referred as loops, they are not traditional loops such as a for loop or a while loop that are repeated until a condition is met or for a given number of times. In Unity, any change that needs to be made to the interface needs to be executed from the main thread. And in our case, for example, the flickering of the stimulus changing from black to white needs to be made and controlled from the fix update function. So these loops will be controlled from that function, and this function will be constantly calling these two other methods. Not that these two methods are loops that are repeatedly being executed by themselves. I don't know if I'm making it clear. We won't go through the whole script, of course, of the manager because it will take too much time. But we will focus on a few key functions that I believe they are essential and play an essential role for the app implementation. First, I like to show the onParameters_ready method. This because here is where the matrix of several commands is actually created. As we saw earlier in the scene, there was only one command, and obviously this is not what we want for a functional speller. Therefore, additional commands must be generated automatically. The onParameters function sets up the scene according to the user-defined configuration. So the user configures whatever in Python through the Medusa platform, and this information is sent to Unity, and in this function, the parameters that the user has chosen will be applied to the scene. In between those parameters, there are the end rows and end calls, which define the size of the matrix and how many commands the user wants to place. So based on these parameters, a two-dimensional array will be created to position each command in one of those of the positions of the array. So what will happen in here is that when this geometry is created and instantiated with the given size, we will iterate through each row and column of the matrix, and we will instantiate the cell object we've seen in the scene. We've only seen one cell, but through this loop, we will duplicate, instantiate this same game object in several repeated times. Once we have created this new game object exactly the same as the main cell we've seen with the letter A in the scene description, we will configure the parameters related to this command, which could be the label it has, the sequence, and the time lag specific to that command. And finally, when we have defined all the commands, we will place them so that they are distributed, evenly distributed through the whole screen. Now we're going to take a look at the fix update function. This function is called at regular fixed time intervals as part of Unity's physics update loop. and the time between its call is determined by a value, the time fixed delta time. This value in our case will be defined in the ons parameter ready, the function I've just showed, according to the frames per second resolution that the user has chosen. So time fixed delta will be set to 1 divided by this frames per second resolution variable. This function acts as the main control loop of the application. It's where the system repeatedly calls the train and test loops depending on which mode of the application we are. And if you remember at the beginning, as a strength of Unity, I've mentioned the possibility to adjust or control the refresh rate of the monitor. And this function is what makes this possible. So this is a crucial function for developing c-VEP spellers or c-VEP-based BCIs in general. And now moving to the training and test loops, the train loop that will be repeated as many times until the end trials set by the users have been done. What will happen during this loop is that the target will be highlighted, the command the user has to pay attention will be highlighted, then it will go through a standby moment in which the matrix is just showed without flickering or anything highlighted, and then the flickering will start it to until end cycles, which also are defined by the user, had occurred. And for the test loop will be running always that the user or that the app is functioning in that mode until the end selections that the user wants to repeat are completed. And in this case, we will have first the standby state in which the matrix is just shown as it is, no flickering, nothing highlighted, just normal. Then flickering will start it, and the visual stimulation, which also will happen for end cycles defined by the user. In this case, will be end test cycles. And with these test cycles have finished, Unity will send to the platform a message saying process please, so that the trial is decoded in the kernel, and it returns the letter or the command that the user has selected. When this command is sent back to Unity and Unity has the coordinate within the matrix of which command the user has selected, this result will be highlighted. So we are reaching the end of our presentation, and for this last part, I'd like to briefly share the research that we've been conducting with this application, and as well the next steps that we are currently implementing. In our latest research, we have studied the effect of stimulus opacity in c-VEP-based BCIs. To make this possible, in version 3.1 of the c-VEP speller, which is now publicly available, we introduced 2 new features. First, adjustable opacity, which allows users to customize the transparency of both the cell image and the command test. And second, we improved the background configuration, which now supports not only to change colors, but also to upload any image the user wants as background scenario. And these changes in the app allowed us to evaluate how the stimulus opacity influenced c-VEP performance and user experience also. We conducted an experiment with 10 participants across 6 different experimental conditions, and the results were quite interesting. We found that introducing some transparency in the stimuli enables a smoother integration of the matrix of commands into the background, which is important if we want to introduce these matrices of these spellers into realistic environments. And moreover, this transparency Moreover, we found that this transparency, as long as the white and black contrast was preserved, did not reduce the accuracy, but it significantly decreased visual fatigue. So it improved the overall comfort of the users. In this picture, you can see the 6 experimental conditions we evaluated. Some of them with the realistic scenarios, another with a plain scenario, 100% opacity and different levels of opacity gradually being reduced. And what we found is that the condition that offered the best balance between user experience and system performance was this one on the top right corner, corresponding to 100% opacity for the stimuli when they were black and 50% opacity for the stimuli when they were white. This study has been published this year in the journal Biomedical Signal Processing and Control. So in the paper, you can find additional details about experimental protocols, the analysis methods, and the main findings of our research, in case you're curious about it or you want to know more about it. And also, I'd like to share with you some of what's coming and the direction of our work is currently taking. Right now, we are focusing on developing a generalized solution. Our goal is to make the c-VEP speller a truly versatile tool for c-VEP-based BCIs, one that can be easily configured and can support a wide range of different experimental setups. To achieve this, future versions of the applications will include the option to select different stimulation sequences, not only M sequences, either binary or non-binary, but also, for example, burst codes. Then we also aim to expand stimulus design flexibility, offering both predefined configuration from previously published stimulus design, and also, we want to include the freedom to customize the stimuli completely by the user, allowing any image, any color, or any texture to be uploaded as a stimulus. And finally, we plan to integrate multiple classification methods supporting both template matching signal processing methodologies, but also bitwise reconstruction approaches, relying also regarding both in machine learning or deep learning. And to finish, just as a reminder, any new updates or developments, including everything we've discussed today, as well as other BCI applications on other paradigms as motor imagery or neurofeedback, can be found and followed from our website. And that's all from me. Thank you very much for your attention, and I'll be happy to answer any questions that you may have.
Thank you, Anna. That was a really great presentation, very technical presentation to show the possibilities of the usage of Medusa with also different EEG devices. I remember being there in Valladolid, and I was pretty impressed by the amount of different possibilities you have, not only for programming, but in terms of usage of, for example, the unicorns, the g.tec devices, the USB amp, the Nautilus. So your system seems to be a very broad platform. Do you have collaborations with other universities to develop more applications, or you're currently developing your own on the shop?
We have some collaborations also with other entities here in Spain, some with some businesses or others with some universities. We are developing new applications as new projects emerge and new needs also appear. But also at the same time, we are working on our own applications for our own use and, for example, for our PhD development or for our own research needs.
Yeah, it's really cool because nowadays there seems a lot of interest in neurofeedback, And for the unicorn, you have a really nice neurofeedback application on Medusa. It's something that I always recommend to the people because it's ready to go. Just need to get a g.tec device, just plug it in into your software, and it's working. So
Yeah,
it's very
I
nice.
think this is like a great thing because either you want to develop new things, you can adapt them and create new things. But also, if you are not in that development booth and you just need something ready to use and something that is intuitive and goes directly to the experiment, the applications that are offered at the website are already mm, ready to use, and they offer different things. They apply to different BCI paradigms, not only spellers or c-VEP, but also neurofeedback, as you said, or motor imagery.
Yeah, this is a really broad platform. We have a question from David Fields. In the last masterclass, Python and Unity, Eduardo mentioned that the new release of Medusa would be officially launched soon. I'm looking forward to it. Do you have any insights about when the new version is going to be released?
Yeah, we're working on it, and hopefully it's soon released. We are working hard for that, but I cannot say like a date exactly, but we are hard working on that so that it's as soon as possible released.
Still a secret then.
For now, the pre-release is already available, but we are working to make the official 2025 release available.
Oh, great. So David can just talk with Eduardo and maybe get the pre-release to test it out. So another question from anonymous attendee: when creating custom c-VEPs or speller grids, can you use any type of visual unique images, or is there research to suggest a more limited standard set for better accuracy?
Um, if you mean like the stimulus, they for in the version that is right now updated, the last version, it doesn't offer to upload unique images, but we are working on also for our next publications. We are working so that any image can be uploaded, so it's fully customizable for the user. You can upload whatever you want, and whatever you have downloaded in your own computer as an image. You can use it for stimulation and also for the background. So you can. This will allow, I think, to make any experiment with this application because not only you can use, for example, black and white flickering, but also grating stimuli like the gabber or the Ricker. And even if you want to invent new stimulus and you have the image for that stimulus, you can put it on the stimulus and customize each command for having different images on them.
Okay. You shortly mentioned, and I also heard about it, that you're working in future on also including FNIRs. Do you have any particular applications that you're planning to have on Medusa? And are you planning to have both EEG and FNIRs or just FNIRs?
In the integration of FNIRS and EEG, we are working in a cognitive load
Mhm.
monitorization. Like for cognitive load monitorizations are the first pilot studies we are doing in the integration on both. So not in the application I've been showing today. And we've just tested it with few users and we acquired the FNIRS so recently. So it's in its first stages by the moment. By hopefully we can extend that kind of studies and test it with broader population and with more people to also test it and acquire a better research combining those two neuroimaging techniques.
Yeah, absolutely. Yeah, it's been a very fantastic work that you guys have been doing in Valladolid. It's pretty good to see that you have created a really nice, even though it's a closed platform, it's not closed from how you interact with it. And it facilitates a lot of the process of data acquisition and pre-processing or real-time processing in the meantime. What is your experience from the users? So what is the most or the biggest feedback that you get from the users on how they use
Mm,
Medusa?
I think that people find it easy to use and quite intuitive. People, even not knowing anything about programming or not being engineers, has been tested the application or been near our experiments, and I think they can also understood what's happening, and there's no this language barrier on what's happening on how to manage it. So it's quite intuitive. It's just a platform that involves many applications and is all managed through buttons, play, pause. So it's quite easy. The configuration of everything. You do not have to hard code anything or know anything about what's behind, which is of course much more complex.
Yeah. What are your words to convince someone to start using Medusa and stop using MATLAB?
I don't know. I just say that I just encourage people to test it and see it by themselves. So they will probably see many of the advantages it, it can have for many research needs. Of course, there are some things to improve on. Maybe someone doesn't encounter a 100% solution, but maybe it's a 100% solution and there's only 10% remaining to do. So that's also an advancement.
And it's also a always developing platform. So I guess you guys will never
Yeah,
stop.
basically because it's the platform we are working on and we need it for our own research. So we can't stop creating and updating it.
That's very good. Means that you are developing in projects as well. Yeah, fantastic. Thank you so much, Anna. It was a really great pleasure to have you in our masterclass. And thank you so much for the presentation and to let people know that they can just use Medusa for their own projects. And as I said, they should just try it. It's for free. It's available. They just should go forward and do it.
Thank you for the invitation and thank you all for your attention. Thank you very much.
Thank you, Anna.